Hi, my name is Rick Hedgman. I'm your professor for Management 602, Production and Operations Management, and today we're going to be talking about capacity and queuing. Now, in advance, I apologize for my voice. I'm still sick. Those of you watching this know that I've been sick for a while right now, and so the truth of it is that this will replace a face-to-face lecture. Um, so let's go ahead and get started on capacity and queuing. Take a look at this particular graphic, and you can see something probably not so surprising to many of you anyway, which is that when snow comes, the capacity of parking lots gets reduced. The lines for the spaces in which people ordinarily park tend to become obscured. Lines tend to start drifting. People tend to start parking in places where they wouldn't ordinarily park. But overall, the capacity tends to be reduced. So there are many reasons for loss of capacity. Consider the current situation for this class at Forte State University. Ordinarily, this would be a face-to-face only sort of course, but this semester it's hybrid. It's hybrid in part because the room capacity has been severely reduced due to COVID and the necessity for social distancing in the classroom. So the ordinary capacity of the classroom is about 64 students, plus somebody sitting up in front. During COVID, the capacity of the room was only about 15 at any given time, plus the instructor. So you can see a loss in capacity from ordinary capacity or normal capacity to the actual capacity under the present circumstances. So we have two types of capacity at least that we can identify. One is the design capacity. So relative to the classroom that we're in for Management 602, the design capacity is for 64 students, or 64 people in general in the course, plus one person up front delivering a lecture. The effective capacity right now is much less. It's much less because of the need to social distance under COVID restrictions. So what impacts the design capacity to reduce it to what is called effective capacity? Things like routine maintenance, being affected by the resources that are allocated versus the ones that are needed. We can only sustain so much effort. The reality of it is that nobody can work at 100% all the time, for example. Or the output level that the process is designed for may be less than what the design was for. So, lowest cost per unit. It could be that it's better to produce fewer, not more, in order to get the lowest cost per unit. Producing more could lead to things like increased maintenance cost, increased human capacity cost, that is, having to hire more people, putting on more shifts, hence increasing utility costs, things like that. So, lowest cost per unit could be better if we didn't increase capacity, if we didn't do something like add shifts or people and so on. So let's talk about utilization and efficiency. Capacity utilization, is the actual output divided by the design capacity. And then the efficiency is the actual output divided by the effective capacity. And you should see a difference between those two. So generally speaking, the efficiency will be at least as high as the capacity utilization, typically higher. So efficiency can actually be more than one, but not usually for very long, because we can't typically sustain the sort of effort that it requires to do that. Not only that, but as people tend to work more, machines tend to work more, you tend to have a tendency toward what's called entropy. Things wind down, they become less efficient, they erode. That includes eroding our attention, for example. That's one of the reasons why, ordinarily speaking, things like a census are not as accurate as a sample result, at least not for very, very large populations. So oftentimes we can produce more accurate results by using a sample and then estimating than we can from trying to count everything. And the reason that occurs is because of things like fatigue and just errors stacking up upon errors when you're looking at things like multi-millions of sorts of inspections or census ballots that have to be counted and so on. So consider the Boeing 747-400. The design capacity of the Boeing 747-400 is 140 tons, but it could be that the effective capacity is only 124 tons. Why? Because we may carry less inside the plane than its design capacity due to the fact that in bad weather maybe the landing gear could fail. So with a 120-ton load, what are the two sorts of values that we have? Well, we have the utilization, which is the actual load divided by the design capacity. That's 120 over 140, or 0.857, about 86%. Whereas the efficiency is that actual load divided by the effective capacity, 120 over 124, almost 97%. Here's an example for this room that we just talked about. Well, I shouldn't say this room, this is my home office, but for the room in which we would ordinarily be having class for Management 602, McCartney Hall 104. The room design capacity, 64 persons. The effective capacity, under COVID restrictions, only 16 persons. So if we have, say, 15 people that are enrolled, then your utilization would be only 15 out of 64, or 0.2344. So less than 25%. Whereas your efficiency, your actual enrollment divided by the effective capacity, that's 15 over 16, or almost 94%. We have economies, or what are referred to as economies and diseconomies of scale. So economies of scale are usually benefits that accrue to you as you increase in size. Diseconomies of scale are things that are detriments that occur when you increase in size. So oftentimes what happens is that on the economies of scale side, your cost per unit will become less the more that you make. Your fixed cost will spread out over more units. So for example, if you're charged $10,000 to place an order, okay, no matter what the size of the order, obviously if you can order more, then the cost per unit would be less. Diseconomies of scale, things like congestion, confusion, increase in supervision, trying to just run yourself ragged so that you produce, usually means more fatigue, usually means more maintenance is required of machinery and so on, leads to more overtime, to burnout, to mistakes, and so on. I suspect that all of you are familiar with the burnout and mistakes aspect of trying to do too much in too little time. Oftentimes we see that when we say that someone is cramming for a test, or they're cramming for finals, or something of that sort. So what are some break-even points? Well, break-even points are defined as following. So we're going to have a graph. Ultimately, we're going to have a second yellow line that appears on this graph. So we have fixed cost, variable cost, we have a break-even quantity, and we have R, which is the revenue per unit. So a break-even quantity is the amount that we have to order or make to have our cost equal our revenue. After that, we start to make money. So relative to definitions, what are fixed cost? They go by many names. They include, for example, indirect or overhead cost as well. But what they are is business expenses that are not independent on the level of goods or services produced. So they tend to be things that happen over and over and over. Say a monthly rent that you pay, or maybe order placement cost. Marginal cost. What are marginal cost, even though you don't see those used in a formula anywhere? Marginal cost is the cost that arises when you produce one more unit. Okay? One more unit. How much does that one extra unit cost you to produce? Or how much does it cost you to serve one extra customer or one extra meal, or whatever the case might be. Variable costs, on the other hand, are costs that change as the quantity of the good or service that a business produces changes. So variable costs are the sum or the total of the marginal cost spread across all units produced. And when you add fixed cost and variable cost, then you have total cost. So that break-even point is where those two lines cross. How do you solve for the break-even point? Obviously, it'd be nice to know what that is. So for a profit of P, the quantity, the break-even quantity is equal to fixed cost divided by revenue minus variable cost. So let's suppose that for whatever circumstance we're in, we have a fixed cost of $50,000. We have a variable cost of $2, and we have revenue of $10. Now those are $2 per unit and $10 per unit. So the break-even quantity that we need to make or produce is that fixed cost, 50,000, divided by R minus VC, R10, VC 2, or 8. So 50,000 divided by 8 is 6,250 units. Once we get to 6,250 units, we're breaking even. Less than that, we're losing money. Much less than that, we're losing more money. More than that, we're making money. Actually, let me revisit that last point. So look at the discrepancy between the yellow line and the red line. So, and then look to see where the break-even point is. And what you can see is that for any quantity less than the break-even point, that our revenue is less than cost. And in fact, for very low quantities, it's much less than cost. When we get to break-even, they're equal. So cost and revenue are equal to one another. Anything after that represents profit. Notice that the profit margin increases as the number of items produced exceeds more and more the break-even quantity. Sometimes we make capacity trade-offs. So it could be that we can make 120,000 four-door cars, or we can make 150,000 two-door cars. So the legitimate question is, can't you do some mixture, some blend? That would be a capacity trade-off. So if we can produce some sort of blend of four-door and two-door cars, so maybe you can produce 60,000 four-door and 75,000 two-door cars. Something like that. And you might try to reach capacity trade-offs that lead to greater profit margins. We talk about time horizons, and ordinarily speaking, we talk about long-term, intermediate term, and short-term time horizons. So long range, those are things over a year, generally speaking. And that's over a year of acquiring and disposing of production resources. Intermediate range, typically we're talking about monthly or quarterly plans. Hiring, firing, layoff plans, things like that are examples. Short range or short-term time horizons tend to be less than a month. They might be daily or weekly, for example. And examples of processes that we do in the short range are typically scheduling processes, overtime scheduling, worker scheduling, things of that sort. We could add capacity maybe. Adding capacity is ordinarily speaking expensive. And so if adding capacity is expensive, then obviously enough you have to find a way to use that additional capacity to generate enough more revenue to justify the investment, whether it's immediately or whether that's over time. So a few large expansions might be cheaper per unit than many small additions. Larger expansions allow for a clean sheet of paper thinking, redesign of processes. So carrying unused overhead for a long time may never be needed, right? You may never need a large expansion, for example. You may never need to add capacity. You might be able to use what you've got in different ways. So capacity planning. You might look at a conservative approach versus a long-term versus an optimistic approach. Those depend on how reliable your forecasting is and over the term over which you're forecasting. So if I'm forecasting over shorter terms, we would expect our forecasting to be more accurate than if we're using longer time horizons to forecast. But we can determine whatever capacity needs we have for likely levels of demand. And similarly, we can determine a capacity cushion. What does that mean? It means that there may be times when we're surprised. We're surprised because we get more sales than we were expecting, more orders. Maybe that happens, let's say, on Black Friday or around Christmas sales or around Easter sales or around Labor Day white sales, as they're called, for linens. So those things could be. Maybe it's fireworks, and somewhere around Independence Day and New Year's, you see increased demand for fireworks. And so you might be able to, even though ordinarily speaking you're producing at some normal sort of level, then you may have a spike in demand that means that you need to have more capacity, at least in the short run. Maybe not in the long run, but in the short run. So you need to have a little bit of cushion in capacity. So it's oftentimes called just in case. So what are sources of capacity? Well, you might expand facilities. So I think I probably mentioned to you that prior to moving from Idaho to Denmark at the end of 2011, I had done some consulting for a large paper company, a very large paper company that you would know the name of if I mentioned it. And that large paper company, part of the problem that they had is that they had warehouse after warehouse after warehouse after warehouse that was full of paper, full of waste paper. Why was it waste paper? It was waste paper because it was flawed. It was the wrong size. It was the wrong color. It was not quite the quality that was needed. Excuse me. And so thinking that they might someday be able to sell that waste paper at reduced cost, they would go ahead and just store it up. But that meant that they were building facilities to store it in. And we all know that paper over time erodes and deteriorates. So there might be other ways besides expanding facilities to expand your capacity. You know, maybe you go to 2 shifts or 3 shifts instead of just a day shift. Maybe you outsource more activities so that, in fact, you're not doing that yourself now, somebody else is doing that for you, and you're essentially buying capacity from them. Maybe you do training. Okay, so maybe that means that people are now able to work more efficiently and effectively than they were before as a result of the training. Or maybe you acquire faster equipment or more accurate equipment or equipment that produces less flawed output. So those are examples of sources of additional capacity. Let's look at some decision trees that can help us make good decisions as to whether or not we expand capacity or whatever the case may be. So decision trees are just a simple tool that help you consider different possible decisions and different possible outcomes. So we would compute expected profits or consequences, more generally speaking, compute expected consequences of each decision. And then we can choose the decision, if we want, that leads to the highest expected profit. And you can work your way back up the tree. So let's look at a quick example here. This is an example where something has happened and there is an opportunity or the potential at least of suing someone in court, suing another company in court, whatever the case might be. So we have a decision to make. Maybe that decision is that we choose to take our case to court, have it heard there, and a decision rendered by the court or by the jury. Or maybe we've been accepted a settlement and we could take that instead. So the question is, what should we do? Should we litigate or should we accept a settlement offer? Well, let's see. The settlement offer assures us of $1 million or 1 million pounds or 1 million euros or whatever unit of currency you're using. 1 million. Okay, if we decide to litigate, there's a chance we're successful, there's a chance we're unsuccessful. There's let's say a 60% chance that we're successful in litigation. There's a 40% chance that we fail to prove our case or fail to have a convincing enough case to lead to a positive outcome. So if we fail to prove our case, we have all those costs that we've built up of litigation. And let's suppose those are $100,000 that we lose their cost. We chose to litigate. We could have had a million in our pocket. Instead, we chose to litigate. We failed to prove our case. We lost $100,000 in cost. That's possibility. Let's suppose that happens with 40% probability if we litigate. Or if we litigate, maybe there's a 60% chance that we're successful. And even though we have asked for particular damages, we might not get what we asked for, and we might get more than we asked for. So let's suppose then that there is a 30% chance that high damages are assessed, a 40% chance of medium damages, 30% chance of low damages. High damages, let's suppose you get an award of $2.9 million. Medium damages, $1.9 million. Low damages, $900,000. So settlement offer guaranteed $1 million. If we choose to litigate, we could lose $100,000. There's a 40% chance of that. Or there is some chance that we walk away with as much as $2.9 million, $1.9 million, or $900,000. So there's a 60% chance we walk away with something. Okay, the question is how much? So 60% chance we litigate, we win. 30% chance that if we win, we get high damages, or 0.6 times 0.3 would be 0.18 of $2.9 million. 0.6 times 0.4 or 0.24 of $1.9 million. 0.6 times 0.3 or 0.18 of $900,000. So what does that come to? It says that the expected value of litigation is, let's see, a 60% chance of, this is your expected, in brackets, from here to here, that is your expected reward from litigation, your expected damages. So a 30% chance of 2.9 million, 40% chance of 1.9 million, 30% chance of 900,000, whatever those add up to, times 60%. So that is, and a 40% chance that we lose $100,000. So 60% times 0.3 or 30% of $2.9 million is $870,000. 40% of $1.9 million is $760,000. 30% chance, or 30% of $900,000 is $270,000. So if you add those up, those are 1.9 million. So, you know, our expected value of litigation is not quite 1.9 million. Okay? Because there's a chance that we litigate and we lose. Okay? 40% chance we lose $100,000. So that's the 0.4 times $100,000. That's the minus 40,000. So your overall expectation from litigation is 60% of 1.9 million. That is 1.54 million. Okay, minus the 40,000. Okay, so there you go. Or excuse me, 1.154 million. So that's what we have. So we're at about this amount, 1.1 million, unless I made some calculation error anyway. You can verify the calculation. So basically, if you're going to be making a decision The decision that you should be making is, should I take should I take $1 million as an offer, or should I go through the process of litigation? $1 million guaranteed versus anything between a loss of 100,000 and a victory of 2.9 million if I choose to litigate. Overall, the settlement offer $1 million, the litigation offer 1.1 million. We can see that the expected value of litigation, 1.1 million, is higher than taking the 1 million sure thing. So you have a choice to make. Some people, those who make their choices based almost solely on expected values, would say, let's go ahead and litigate. Other people would say, let's make the safe choice and take the 1 million. Which are you? Are you risk averse, in which case you're going to take the 1 million sure thing, or are you attracted to risk, more attracted to risk, more of a risk taker? Well, in that case, you'd be more likely to litigate, but nevertheless, the choice would be yours. Which would you take? What would I do? Well, in this case, truthfully, what I would do is I'd probably take the $1 million. I have a lot more value for $1 million sure thing than I do from the potential of losing $40,000. So that's me. I have, let's see, what is 0.6 times 0.3? 0.18. So I have an 18% chance of $900,000. I have a 40% chance of minus 100,000. I have an 18% plus 40%. I have a 58% chance of less than that amount resulting if I litigate. For me, that's enough to make the difference. I would go ahead and say, I guess I'll accept the settlement. Okay. For other people who $1 million maybe is not much money to, they're more likely to say, go ahead and litigate. Roll the dice. But nevertheless, the decision is up to you. The point of the decision tree is not to make your decision for you. The point of the decision tree is solely to be an aid in your decision-making process. What about retail lines? So in other words, you're in line at the cash register or something like that. So what do you see when you go through the line, let's say at Walmart or the grocery store or something like that? Well, a lot of times as you're going through that checkout line, there are things that you don't actually need that are sitting right there. But they're there. They might be attractive, but you don't need them. And so you end up buying some anyway. Let's say candy or a cigarette lighter or some sort of a seasonal promotional item for a holiday, something of that sort. Greeting cards. Okay. Here's a typical reality. People don't like waiting in line. I don't know how patient you are. I'm not very patient, ordinarily speaking. I hate waiting in line. Therefore, I get bored easily. So I might reach for a magazine or a book while I'm in line. If I do that, I might say, well, I guess I'm going to go ahead and buy that. Okay? So what are some other examples when you're waiting on deposit slips or postal forms or something of that sort? So actually, you're in line a huge part of your life. You're in line at the grocery store. You're in line in a traffic signal. You're on hold waiting to catch a service representative. You are in line just waiting to pay for something at a cash register at JCPenney. So there are all sorts of forms of being in line. You're in line waiting to get into a concert. A big part of your life is spent in line. Well, what might you do if you were talking about the entertainment industry? Maybe you're talking about, let's say, Disney World. So what do they do when you're in line? The answer is that they might do a lot of things to make it seem like the time passed faster. Or there may be some people who are willing to pay a little bit more not to stand in line and hence bypass the line, so to speak, or what we call jumping the queue. So how do you jump the queue? Well, maybe you can do some things like pay a little extra. You pay a little bit extra and you get priority. Okay? Priority boarding on airplanes. I have priority boarding with United, for example, because I've traveled so much with United. I probably put on 2 million or 2.5 million air miles over the course of my life with United. And I put on probably another million with other airlines. So I've had to do a lot of travel. I don't necessarily enjoy it, but I've had to do it. But I have some perks that are attached to that. Or maybe I get reduced or no baggage fees. So I might get perks. Or I might get a ticket that says, look, this is a really long line, so come back and get in the line. You're gonna get to enter the line anywhere between, let's say, 10:40 a.m. and 11:40 a.m. So it could be that. Okay, there are lots of things that you could do with that time rather than just stand in line. You could ride at the rides, you could buy souvenirs, you could go pick up a hot dog at the theme park. You could do whatever it is that you might not otherwise do. Or what else might you do? Let's say for a couple different rides, it could be that you enter the queue, you go a little ways through, and then there's some activity right there. Or something to watch, some distraction. You go a little bit further, another one. And notice by the configuration of the line also that they typically are able to get more people in the line, more space efficient. Here's another one where maybe you have the same sort of arrangement. So what about the study of lines? The study of lines is called queuing theory. Q is the Q-U-E-U-E is the French word for line. So let's just take a look at some basic results in queuing theory. So there's cost effectiveness that we concern ourselves with. How much money do we lose from people waiting in line, let's say for the copy machine or whatever? What would justify a new copy machine? Notice I misspelled effectiveness, by the way. I should have an E between V and N. Okay. How much money do we lose from bailing out? That is just being there and then all of a sudden people leave. Okay, so what happens there? How many times have you been on hold for something, maybe to make a purchase, and you get so tired of being on hold that you just say, forget that, I'm going to do something else instead, and you never go back to that line. Okay, that's the bailing out that we're talking about here. Study of lines, queuing theory. And we usually look at least two aspects of study of lines. We look at arriving in line, and we look at being served. So what are some of the service differences that you might see? You might see, for example, that the arrival rate is really variable. You maybe can't store the products, yesterday's flight. Service times are variable. You get people who are just pushy, serve me right now. Sometimes rates change quickly. Sometimes we schedule our capacity in just 10-minute intervals, not months. How much capacity do we need? Those are legitimate sorts of questions. So oftentimes we're the problem, or whatever it is that's in line is the problem, whether it's people or something else. Why? Because we don't arrive in a totally predictable manner. Customers arrive randomly. Okay? The time between arrivals is called the inter-arrival time. Enter inside, literally the time between arrivals. And inter-arrival times often have what's called a memoryless property. So if on average the inter-arrival time is 60 seconds, and it's been 5 minutes since anybody arrived, that doesn't change the probability that somebody is going to arrive in the next 60 seconds. It remains at 60 seconds. So that part does not change. And then there's variability in flow, which usually means that you need some excess capacity. If you don't have excess capacity, what happens is that on occasion at least the line builds up and then the frustration starts and so on. So memoryless property, we're talking about the so-called exponential distribution. Now, I will tell you that as a statistician who for many, many years, decades, taught business statistics, that had you gone through a business-focused statistics course, there's a very, very good chance that when you went through probability, that you would see two distributions presented side by side. You would have seen probability distributions that were continuous ones, like the normal distribution, for example, is continuous, or you would have seen some discrete ones, the binomial distribution, the Poisson distribution, some others. Okay. You would have seen different probability distributions. But if you went through a business statistics course, a reasonable thing to do inside that course is that you're going to see the exponential distribution, how people arrive in line, or how things arrive in line. You're going to see the exponential distribution taught almost side by side with the Poisson distribution. How those things are served, people are served once they are in line. So the exponential distribution is a continuous distribution. The Poisson distribution, only discrete outcomes are possible, is a discrete distribution. So let's see what we've got. Let's suppose that the in-arrival time is literally the time between arrivals. We've seen that. The memoryless property means that it doesn't matter how long you've been waiting. If the average wait time is 5 minutes and you've been there 10 minutes already, then the expected time before the next arrival is still 5 minutes. So what does the exponential distribution look like? There are a couple different ways that you could write it down, but typically it would say that the function is lambda e to the minus lambda t. So lambda times e to the power of the negative lambda t. Remember what e is. E is called a natural base. Sometimes it's written as 3 letters, exp, for exponential. And its value is approximately 2.7183. So E is approximately 2.7183. Now, what this looks like depends on the value of lambda. T is time in this case. We could have used anything. We could have used X. We could have used Y. I have T here simply because so often the exponential distribution is used in conjunction with time. So lambda e to the minus lambda t. What that is the height of the function at any given time. And what that function looks like if you were to graph it depends on the value of lambda. Okay. Now what we're really interested in with the exponential distribution isn't so much what is the height of the curve. What we're concerned about are more probabilities. So for example, what's the probability that t is less than time 2? Okay, so that's what this is capital F. It is the probability that the time it takes is less than or equal to t star, where t star is any particular value. Say 5 minutes. Okay, and that is equal to 1 minus e to the minus lambda times t star. The mean of the exponential distribution is 1 over lambda. Its variance is 1 over lambda squared, so its standard deviation is just 1 over lambda. Its mean and its standard deviation are the same value. Okay, and it will tend to look like that. Now, that is for how things arrive in line. Let's say how people arrive in line. Let's look at how they're served once they are in line, the probability distribution for being served. And that's called the Poisson distribution. Simeon de Poisson was an incredibly successful and famous French mathematician, basically from the Napoleonic era, and he worked with many of the famous French mathematicians of the day. He was one of their proteges, and himself produced his own proteges. But for the Poisson distribution, if we assume And there are many applications for the Poisson, so I'm only talking about application of the Poisson distribution in queuing theory. Okay, so it tells the probability of a given number of arrivals during some period t. So I may be saying, what's the chance that 3 people arrive in a 10-minute period? Okay. Now, here is a brief paragraph about some of its early derivation, but here's the actual formula you use to compute Poisson probabilities. Okay. The probability that the number of arrivals in line, or the probability that the number of items with the trait of interest is equal to some particular value, let's say x star. I would substitute in, for x here, I would substitute in that particular value, x star. So mu to the x star, e to the minus mu, where e is that same value, 2.7183 approximately, raised to the minus mu, divided by x factorial. And remember that factorials, so for example, 5 factorial is 5 times 4 times 3 times 2 times 1. Or what is that, 120. Okay, 3 factorial is 3 times 2 times 1, 6. 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, whatever that is. 0 factorial is 1. So if you've forgotten a little bit about factorials, remember that 0 factorial has the value 1. Now the truth of it is that even though that's how you see factorials presented in an introductory statistics course, the factorials are something that represent the area under a particular curve. So when we say 0 factorial is 1, we're not saying that to make something convenient for ourselves. We're saying that because it's true. So there's no hocus pocus, no magic involved. 0 factorial is in fact 1. And that's provable. You just have to have enough calculus to be able to prove that. Okay. 1 factorial is 1, 2 factorial is 2, 3 factorial is 3 times 2 times 1 or 6, and so on. Note that I could write this another way if you don't like negative exponents. If you don't like negative exponents, you could write this as mu to the x divided by, and then on the bottom of the fraction you would have e to the positive mu times x factorial. The mean of the Poisson distribution is mu, the variance is mu, the standard deviation is square root of mu. So the Poisson distribution is the only distribution for which its mean and its variance will always be exactly the same value. Okay, if you want to read a little more about Poisson, and it's actually a very interesting history, more especially if you have some interest in mathematics, but in general it's still an interesting history, then you could find out a little bit more about him right here. So here are some graphs for different values of, let's say mu. I could have used the symbol lambda instead of mu. I could have used any symbol I wanted right here. In fact, in quality control applications, it's oftentimes that we use the letter C instead of the Greek letter mu. But I can use any symbol I want. On the next graph, which I just picked up off the internet, they're using the symbol lambda. So for the Poisson distributions, here's what the distribution looks like. The probabilities of different values of x, roughly for x up to about 12. Notice that if the mean is 5, that the highest probabilities are around 5 and 6, and that it tapers off very quickly or drops off very quickly on each side. That for a lambda of 15, notice that again it peaks around 15, 16 in that area, and that it drops off very quickly around that. Let's see, the mean is 15, the variance is 15, the standard deviation is square root of 15, a little less than 4. The Poisson distribution is like virtually every other probability distribution. Most of the probability, and hence most of the actual outcomes, reside very close to whatever the average is. Well, if the average is 15 and the standard deviation is 4, a little less than 4, then you're going to have most of the outcomes between about 15 plus and minus 4. That is within 1 standard deviation each side. And lo and behold, you can see that we have that. Between about 11 and 19, we have most of everything that happens. Between the mean and 2 standard deviations, 15 plus and minus roughly 8, notice that you've got almost everything. So in theory, any positive counting number plus 0, 0, 1, 2, 3, 4, 5, 17,627,108 would be possible. But in practice, the actual values you see for the Poisson and for virtually any other distribution are always, with very rare exceptions, really close to the mean, within a few standard deviations either side. Notice that you started out, by the time you had a mean of 5, looking semi-normal overall if we were to connect the dots. By the time you got to 15, it looks real normal. Notice it's looking more and more normal as the mean increases. Okay, that is the normal distribution. There are conditions under which the normal distribution can be used to approximate Poisson probabilities. Why would you even want to do that? Well, you might want to do that because using the Poisson formula is a little bit of a pain in the neck. Using normal tables or something like that is trivial. So let's see. How about some assumptions of memory lists? Let's suppose that we have an exponential arrival rate of lambda equal to 10. Okay, so maybe 10 customers per hour arrive. That would mean that the inner arrival time would be your time frame divided by 10. So if that's 10 per hour, then that's an hour divided by 10, or 60 minutes divided by 10 would be 6 minutes. So approximately 6 minutes between arrivals on average. Of course, what we're not really seeing is every 6 minutes somebody arrives. Another 6 minutes, somebody arrives. Another 6 minutes, somebody arrives. Remember, people are arriving randomly. So maybe in the first 6 minutes you have 4 people arrive, and then you don't have anybody else arrive for 18 or 20 minutes. Right? But on average, the inner arrival time is 1 customer every 6 minutes, or 10 customers per hour. So we better have a service rate that is higher than the arrival rate. If you don't have a service rate that is more than the arrival rate, then your line over time builds up and up and up and up and up until you have this infinitely long line, or until you start saying things like this. People go for COVID shots. At the end of the day, they're still in line, but they're done dispensing COVID shots, COVID vaccinations. Therefore, sorry, come back tomorrow. Hope you find your place into a good place in line. Or people start defecting. So they want this hamburger, and I've done this I don't know how many times, where I've been in line at, let's say, McDonald's, and I get tired of waiting in line, so I go over to Burger King, or vice versa. Okay, why? Because I'm impatient. I defect. But I need to have, in any case, the service rate be more than the arrival rate. If not, then I need to consider things like, how do I add capacity? So how is it that I could increase my service rate? Do I hire another person? Do I add another cash register? Do I add another ATM machine? Whatever the case might be. So if the exponential service rate is, 12, that says I can serve 12 customers per hour. So the service time would be 1 hour divided by 12, 1/12 of an hour per person, or 5 minutes. I could have written this as 5 minutes. And the utilization is what? Is the lambda divided by mu. We sometimes symbolize that by the Greek lowercase letter rho, lambda over mu, or about 0.833. So you might ask yourself, what's the average number of items or people in line in the queue? And the average number of items on the line is the length of the queue. That's what L is for, length of the queue. Is equal to lambda squared divided by mu times mu minus lambda. So if we were looking at the prior slide, this would have been 10 squared, or 100, and this would have been 12 times 12 minus 10, or 2, is 24. So this would have been 100 divided by 24, whatever that is, 4.17 approximately. So on average, a little over 4 items in queue at any given time. What about the average number of people in the entire system, including those who are actually being served? So that would be the length of the queue plus lambda over mu. This lambda over mu is the thing that we called rho. So this would be length of the queue. If I was using the 10 and the 12 for lambda and mu, then this would have been the one that we just came up with, about 4.17. This would have been 10 divided by 12, or approximately 0.83, the length of, or excuse me, the average number of items in the system itself, length of the system, if you will, would have been 5. What's the probability that there are no customers in the system or no items in the system at any given time? Well, that's just using the Poisson distribution, the probability distribution. That would be 1 minus lambda over q. In this case, that turns out to be 0.167 approximately. So there's almost a 17% chance nobody's in the queue at any given time. What's the probability of having exactly n customers in the queue? It turns out to be the probability of 0, notice exactly n, not at least n, not n or less, exactly n customers in the queue. 6 customers, let's say. Then it would have been the probability of 0 times lambda over mu to the n power. So if you were talking about exactly 6 customers in line, this would have been this number, 0.167 as I recall. 10 divided by 12 is 0.83. 0.83 to the 6th power, whatever that is, times that P0 value. What's the average time that you're in line? Right? The average time in the queue. The average time in the queue is LQ over lambda. So remember a minute ago, if we were using the 10 and the 12, that LQ was about 4.17 and lambda was 10. So it'd be 4.17 divided by 10. Notice that that was customers and the lambda was in minutes, so you would have had that. Lambda was in 10 per hour, sorry. 10 per hour, and this was 4, so about 0.4 hours, excuse me. About 24 minutes is what you would have had, right? 4.17 customers divided by 10 customers per hour would be about 0.4, a little more than 0.4, 0.417. That would be about 24 minutes. I'm just rounding, doing math in my head. How about the average time in the system? WQ, 24 minutes, plus 1 over 12, right? Mu is 12, so we're serving about 1 person every 5 minutes, plus 1/5 of an hour, so 24 minutes, or 0.4 of an hour, plus whatever that was, 1/5 or 1/12 of an hour, 5 minutes. 24 minutes plus 5 minutes is about 29 minutes. So when you call and you're put in a queue for service, and they say something like your expected wait time is 28 minutes, or 29 minutes, or 37 minutes, or whatever the case might be. They are using formulas like this to estimate for you, right? Notice these are all estimates. That's why they say average time or average number. They're estimates, and they're using formulas like this to deliver those. So as an example, customers arrive at your service desk at a rate of 20 per hour. You can help 35 people an hour. So what percent of the time are you actually busy? What's your utilization? How many people are in the line on average? How many people are there in total on average? Ah, there you go. Utilization, 0.571. So we have more than enough capacity under normal circumstances, right? 20 over 35, 20 arrive, we can serve 35, no problem. So we have plenty of capacity. Average number of people in the queue. Okay, lambda squared, that's 20 squared divided by mu times mu minus lambda, that's 35, times 35 minus 20, so times 15. 35 times 15, whatever that is, that's 525. 400 divided by 0.525. So your average time in line is only about 0.762 of an hour, or excuse me, of minutes. So you're not going to be there very long at all. And then if you look at this, now that's the average time in line. That's not your average time being served. Okay, that's your average time in line, 0.762. Not bad. And the average number of people in the system, LQ over lambda plus divided by mu. So about 1.332. So at any given time, there's a good chance that that if you arrive, either you're served immediately or you're the next person in line. Maybe too deep, something like that. How long is the wait? Okay. Here it is, 0.762. We have that for LQ. Lambda is 20 per hour. Waiting time, 0.762 over 20 is 0.0381 hours, so about 2.29 minutes. Not bad. What about the total amount of time you spend in the system? Well, we have WQ, 2.29 minutes. Sorry. And then we have the other part here that says that there's about 1.714 minutes otherwise. So about 4 minutes. And all we're doing is plowing through these sorts of formulas that you've just been seeing. So my advice to you would be to spend some time on the distributions. So on the exponential distribution, take a look at it. Spend some time on the Poisson distribution. So you may or may not have seen the exponential distribution in your statistics course. You should have seen the Poisson distribution without fail. So I would work through the examples that you have, and then I would caution you that you need to be careful about keeping track of your units. So if you're going to work in hours, do everything in hours. If you're going to work in minutes, do everything in minutes. If you're going to work in pounds, don't do it in pounds sometimes and tons the next. Right? You see the point. Keep your units of measure the same throughout working through the formula. So in other words, if you're saying the exponential arrival rate is 10, then that's 10 per hour, but you can either say 10 per hour or you can say every 6 minutes somebody arrives. Okay, so that's what you're going to have to be looking at. So all in all, here's what you should have learned. That the memoryless property means that you've got an exponential distribution, exponential arrivals. You have Poisson arrivals, exponential service. So the results hold for simple systems, just one line, one server. Once you get past one line, once you get past one server, then things become actually dramatically more complicated on the math side of things. Okay, on the math side of things. But in terms of getting just some basic insight into queuing theory and the study of lines, what we've done here will give you some of that basic insight. So thanks very much, and we will talk a little bit next time.